Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad you've taken the time to join us today as we look at our topic of of improving production efficiencies by implementing a screw counting process. And so as we begin, we typically will start our presentations, if you've been with us at any point, highlighting some of the challenges and the torque failures and risks that go along with doing a fastening process. And the most influential one is going to be the human error, or the human that is doing the actual operation, and their ability to influence what happens during that process and how errors can inadvertently happen. And today's topic kind of deals with moving the operator into a way of being able to do the application efficiently and knowing that they're doing it correctly as well. And so when we look at some of the common tightening failures that go along with that can be produced by the operator, over tightening is one of those scenarios, whether that's dealing with a hand tool or a torque wrench. Could also be using a power tool but in the wrong spot. So over tightening can be an issue. And then the opposite of that obviously is under tightening. And this can happen with the operator not fully allowing the tool to reach its torque if we're talking about a power tool. But again, both scenarios, under tightening and over tightening, leave the application subject to failure, because with an over torque type of issue, we have a lot of tension that is going to be on the fastener itself. And if that fastener has been stretched to its yield point, any type of shock or vibration can cause that fastener to fail. And then we will lose our clamp force. And then under tightening, if we don't have enough clamp force in there, and that may allow the components to move, we could see failure there. So over tightening and under tightening are big risks. When it comes to the threaded fastener, if there is a cross thread that may be happening, and that could be with the use of a really fine thread on a fastener, could be the use of a high RPM style of tool. But cross-threading is certainly going to allow the tool to reach its torque, and the operator will get a signal that the tool has torque, but it's not fully seated correctly. Next is going to be missing fasteners. So if the operator is going through an assembly and skips locations, or misses the fastener altogether, this obviously is one of those risks. And so how can we kind of safeguard against some of these fastening failures? And so this is what our topic is dealing with, again, on how we can move the operator into a way of being able to complete the operation without being too cumbersome, but also giving them feedback on making sure that the operation is being done correctly. So with the use of a screw counting feature that does give you the ability to error proof the actual assembly, this is giving you a couple of different things to knock off the list of items that we want to check for. First, the screw counting, which is kind of self-evident. We want to make sure that all the fasteners within the application get done correctly. And then the error proofing process gives us the ability to detect certain fastening errors and does not count those. And so that gives the operator the opportunity to redo those fastenings to make sure that they move through the assembly correctly. This tracking each fastener can be done with a couple of different types of screw counting features. and they may be differently done through whether it is a location-based process or just a generic looking for a good signal of rundown, but that gives us the ability to track each fastener within the process, allowing us to detect if there is a fastening error at that location or at that fastener. Then this alerts the operator. The operator can go ahead and take care of it right away because rework and missing items are very expensive. The rework, obviously, if the part gets scrapped or just the time and the labor to go ahead and do the rework can be expensive. If this component goes to an end user or to a contractor, and that then needs to be redone, or if there's some other paperwork that may need to be done with that, obviously that takes up time and money as well. So anytime we can handle an error at the spot and take care of it, that is always a good thing for us. And so this kind of helps to eliminate some of the operator influence that they may have as it regards to the fastening, and also will assist in the ability to communicate with other line control devices or even a PLC if we want to do batch counting to alert that an assembly has been completed. These types of things can be accomplished with the use of a screw counting system. So what are some of the detectable fastening errors that we can detect? Well, the first one we'll look at is going to be the actual length of a fastener. So if you have an application that has the same screw, could be the same torque, obviously the same fitting, but the lengths are just different. If those get put into the wrong position, we're going to see some failure. So we do have that ability to be able to verify that the correct fastener length is being used at a specific application site. Next is going to be thread pitch. If there is a fastener that does have a different thread pitch, we'll be able to detect that as well. If a fastener gets partially torqued or doesn't get fully seated, we'll be able to check for that error. And this could be just the operator lets go of the trigger when we're talking about using a power tool and doesn't allow the tool to reach the actual torque, and they just move on. But we can detect for that. If there are missing components, so maybe you have a washer stack or another component that needs to be placed with the fastening, if that is not there, that's going to change the characteristics of the actual rundown. So we would be able to detect for that type of fastening error. And then, as we mentioned earlier, any type of cross-thread event that would happen, we would be able to check for that, because that's going to simply bind up the fastener right at the very beginning of the rundown, but it will allow the tool to reach the torque value and get a signal that way. But if we detect that cross-thread event has happened, then the operator can be alerted. There is a cam mount situation where maybe the bit just comes off of the fastener. This could be true with some slotted heads or some Phillips bits. And again, the operator may not necessarily be paying attention. The tool cams out, and then the operator moves on without fully seating that fastener. And then there are strip fasteners as well that we can detect. This is very helpful if you're dealing with self-tapping applications, things like that, where you may see a stripped fastener. But again, the operator may let go of the trigger, even though the fastener is stripped. and again, we have no clamp force within that joint that we are looking for. And then finally, if the operator is doing the application into a recessed area where they don't necessarily have the ability to see what happens, if any of those previous events happen, we would be able to detect if there's an error within a recessed type of application. So that's going to lead us to our poll question for today. So let's go ahead and we can launch that poll. And the question is, what common fastening failures are you experiencing within your application? So we'll go ahead and give you a few seconds here to take a look at that and run that down. And we'll see what we get there. All right. Thank you very much for participating in our poll. The leading answer here was screws not being fully seated, followed by missing screws and stripped fasteners. And so thank you very much for participating in that. And let's go ahead and continue with some of the screw counting features. We've kind of touched on them as we've gone through the presentation, but there are different screw counting options that may be better in one scenario than it would be in another scenario. And the first one that we'll take a look at is going to be the Scout 2 screw counter. And this is the one that we'll be using in our demonstration portion for today. But this unit allows it to be connected to a number of the Mountz electric drivers, where it's connected to the transformer, and it allows the fastener to be measured for a specific application in milliseconds. And so we can create what would be an acceptable window for that particular fastener. And there are different profiles that we can store within the unit. So if there are multiple different fastening applications, we can call up that particular program with the use of either the inputs or the outputs, or they can be manually selected as well. But this allows for batch counting. It allows you to be able to signal if there is a no good fastening, or it will obviously tell us if there was a good fastening as well. But we can have up to 4 drivers connected to this unit that can use those different profiles. But that would be done within an assembly process. It won't allow you to monitor different tools at different locations at the same time, but this is designed for more of a cellular type of build solution. But it is going to give us instant feedback on when there is an error, and giving the operator the ability to go ahead and take care of it and fix it right away. Again, we'll go ahead and we'll look at how we program this unit and run through an example of that during the demo portion for today. Next is going to be using the built-in screw counting options that may be within a DC tool type of offering. And so with our EC DC control tools, we do have the ability to add a screw counting feature within that. And along with the error proofing parameters that are in with the fasteners, we have that ability to give instant feedback if a fastening was not acceptable, and we can count that down to get a cycle count and a batch count. So a lot of what we see within the Scout 2 we can do obviously with the DC tool. We do have a different way of monitoring the fastener. We monitor the fastener in the amount of turn or the amount of angle that happens. And so within a fastening, we have the ability to detect if there's a cross thread event, or if there's a stripped event, or a fully not seated event. So this can happen with the use of those different parameters within the programming of the tool to allow us to error-proof the fastening, make sure that that gets counted and it gets counted correctly. And so we do have a couple of different webinars that we have done dealing with this within the EC product, and also with the next product that we have is going to be the DPC Touch. And so we just did one last month on ensuring that we have the correct fastening at for every fastener that gets done. And so if you want to take a look at that one, this one is a very good option if you need a location-based type of error proofing. And so this will only allow power to the tool if the tool is in the right location for a specific fastener. So this really forces the operator to move through a certain pattern. If that fastening does not or is a not okay fastener, the system does not count it, and the operator must get a good signal for that rundown before it moves on to the next process within the build. And so these can be used with the clutch tools like we're using today with the Scout. It can be used with the DC tools as well. And because of the use of the DC tool having multiple different presets, we can also use the location based to change a preset as well. So again, this is just another option that you have within the screw counting process to error proof that assembly, to make sure that the operator gets all of the fasteners done, but they also get all of them done correctly. And if there are different torque values within that particular setup, that can be accounted for and handled through the DPC Touch system. And so if that is something that you want to take a look at, you can certainly do that. Again, we did that last month, and we worked with our mini MD system, which is our low torque driver, but you can check that out when we go. So let's go ahead and move into our demo for today. And again, we're going to be using the Scout. And so our Scout system here is connected to our transformer here, and we have again the ability to have 4 different tools that we can use at one location. I've got our BF 120 clutch driver and a thread block for us. And so let's go ahead and we can jump in. Might be a little difficult to see that. Let me go ahead and add another light here. And well, that doesn't seem to be helping too much, but let's see. All right. Well, what we're looking at here is we have our different programs. So there are 8 different programs that we can use within this. I just turned this on, so we're in our work mode, and the system is ready. We can go ahead and how the system can detect a specific fastener is we can put it into a teaching mode where it's going to measure the rundowns for us, and then we can develop what the parameters for that particular process are going to be. We can add the number of fasteners we want to count, and that way we can then move that through our assembly. And so as I change the menu here, it may come a little bit more clear, but what we can do is we enter in our password into the system. Now that we've logged in, we can scroll through our different modes, and our second here is our measuring. And so at this point, we can go ahead and we can run the fasteners down on here, and it is going to measure the amount of time it takes in milliseconds to run those down. And so I have these fasteners lifted up to a certain point, and so maybe able to see it a little bit better from this angle. But as I run these down, it will go ahead and capture those readings for us. And so we can go ahead and do that. So these are taking right around 480 or so milliseconds. Or 657. Okay, and so if we like that, we can go ahead and accept that, and we can enter that into our parameter. And we can then enter the number of fasteners. And then if we reset, now we can come back out and we can go ahead and run our next fastener group. And obviously we're using a scenario of 4 here. And I think I did not select the correct. Program should be 1. All right. And let's go again. All right. Okay. All right, here we go. Well, I must be. There we go. Okay, let's go ahead and then loosen up these fasteners. And now that we have begun, We just need to make sure we're at the same kind of starting point that we were when we did our testing. When we're doing this with an actual application, it does make it a little bit easier if we are starting with the actual fastener into the application. But you can see that the error that we had here was a time over. So this could be a situation where we use the wrong length of fastener, or it could be a stripped fastener. But again, if I run the tool without it being on a fastener, we get a no torque up error. And if we then go ahead and run it, it's showing that again we're a time over. So and we are still in that same area. Well, this is unfortunate. All right. Well, let's try it again. We'll put this on program 2. And go to our mode section, parameter. There we go. And so if we get a good rundown signal, we get our OK, and then we have our not OK. And then again here we have our time issue. And there we go. We get a cycle complete, and then the system will go ahead and reset for that particular program. Now, this can be, again, controlled by the I/O port. So we've got a 25-pin I/O here. And then we have power that can either be done externally here, or we can run it through from the transformer. So that is how that system works. And you can see there, it's not too terribly difficult to program. It was a little difficult for me to be able to see the actual display. This is a much older demo unit that I have. The newer units have a backlit display that is a little bit more easier to read, especially when I'm dealing with the camera here with that. But all right, so that is the screw count for the Scout. Again, we can detect errors such as the cross-thread event, an item that hasn't been torqued, or gets fully seated. And so with that being the number one issue in our scenario here, if I run this halfway down and let go of the trigger, you can see we don't get any, we don't get a count for that. If I do then come back to it with that, we get our not okay. So if we again begin it from where we started, then we'll get a good count for that that particular rundown. All right, and with that, that's going to bring up to any type of question that you might have, and we'll do my best to go ahead and answer those. So today, Ashley is going to be communicating any questions that we have. So, Ashley, do we have any questions?
Hi, Dave. Yeah, just a few. First question, how many screws can you count in a sequence?
So with the Scout system, you can have up to 99 fastenings for one program. So and there's 8 programs, so you can have each one of those profiles can go up to 99 fasteners.
Okay, next question we have for line control, can you stop a part moving down the line if there's a fastening error detected?
Yeah, so with the communication of the 25 pin IO, we can go ahead and we can communicate directly with a line control device to either stop it, or we could send another signal out that the operation has been complete, and it can go ahead and move the part down the line. So there is that ability to be able to communicate with either a PLC or some other line control devices, or pneumatic locks, things like that, where the part is going to be nested in something, and we need to release it. We can do that after the cycle complete has signal has been given.
Okay, last question. When setting up the screw rundown time, do you recommend doing 10 or 20 test samples first?
So typically, I guess the more the better is going to give you a little bit better accuracy as far as what is the range is concerned. So 10 to 20 is going to be great. But you can always go back into the parameter menu, and you can fine tune whatever those readings might be from when it was measuring. So if you want to maybe tighten up the tolerance a little bit, to dial it the minimum time or the maximum time, you want to make sure that it's not too tight, but it's not too loose to where you're not being able to detect things like cross-threading or stripping. And so you do have that ability to go in and modify whatever settings that the system has produced for a specific profile. So that's how that can happen.
All right, thank you. That's all we had for questions.
All right, thank you so much for joining us this month, and we look forward to seeing you again next time, as we again look at ways that we can help with your fastening processes. All right, thanks very much and have a great day.